Okay, in the previous session, I promised that I'll talk about the some example, especially talking about the mathematical parts of CKKS. So we are talking about CKKS algorithm. That is, again, one of the most famous ones that actually can be used for AI privacy as well. So let's see how that works. I imagine that there is a hospital. So this is my hospital. And this hospital took a CT scan. So I called that CT scan X. And for simplification, I just consider one pixel. Let's say my pixel is only the value for it, or maybe I call it M just to be consistent as just that's a message. So probably that makes more sense. In cryptography, we also call them X as well. So we call M to be, let's say, 0.8, because again, one advantage of CKKS is that we can work with floating point numbers. Now we also have a secret that is only kept with the hospital. It's not going to be shared with the server. And let's say the secret value is 5. And now this is going to be shared with the server. So I just call it, I draw it like this, and I call this a server. So this server has an AI model that can take any input and then can do the diagnosis and can return the result back to the hospital. Again, if you are working, let's say, with an CT scan, that's going to be, I don't know, maybe 100,000 pixels or maybe million pixels. So we have to put them together, and there are techniques for that. But anyway, we'll skip that part right now. And now we need to have also a scaling factor. If you remember, I told you like the message is small, and we have to make it, magnify it or scale it, because otherwise it's going to be lost inside the noise. So I call delta, or the scaling factor, to be 100. So this is the scaling factor. And what else I need? Also, I need a ceiling. You remember, if you remember in previous session, I said like there should be a ceiling. Otherwise, we go like very large number. Anyway, we should have a boundary, and that boundary gonna be here. Let's say 10,000. But of course, we are working with boundaries that are much bigger. But here, for the simplification, again, like a toy example, we call it to be 10,000. Again, this is our ceiling. Ceiling. Great. Now let's start. First thing first, I just changed the color here. First, the hospital need to scale the message. So we take the message, we multiply it by the scaling factor, and that's going to be 0.8 multiplied by 100, and the result going to be 80. Now I need to do a boundary check, and I see that 80 is smaller than 10,000. So this is safe. There's no problem with that. Now, we have to pick a random number, and I call it a masking factor. So let's call it masking factor. Masking factor. And we show it by A. And here we choose that is a random number. We call it 10. And now we need two error terms, a small error noise, that we call them E1 and E2 error. Or let's say call them E0 and E1. And here we choose E0 to be equals to 2 and E1 to be equals to 1. Now we have to construct our ciphertext. So C1 is going to be A plus E1. That here is 10 plus E1, that is 1. So the result of this is going to be 11. and C0 that is actually hiding the message or encrypting the message. So the first one is hiding the secret key. Later you'll see because we have to multiply this by secret key, but C0 is hiding the message. So this is going to be actually minus A multiplied by S, the secret vector or the secret number here, plus M plus E0. So if you substitute all the values, so it's going to be minus 10 multiplied by S, that is 5, plus AD plus 2, and the result going to be 32. So what happens is that now hospital is sending C0 and C1 to the server, that is 32 and 11. Now let's see what happens on the server side. Let's say server side has a neural network model that is a very simple neural network model. You just need to multiply the input by number 2. Okay, so what happens is that server will multiply both C0 and C1 by 2. So first C0 will become 32 multiplied by 2. That is going to be 64. And C1 will be also 11 multiplied by 2, and that is 22. Now you also have to check the boundary. Server must ensure, of course, that the result doesn't hit 10,000. Inside C0 is a small, and C1 is also a small, and all of them, both of them are below 10,000. So the boundary has no issue. Now what happens is that the server, let me scroll down here. If I can scroll down. Maybe I take this up. Yeah, that's better. Now let me go to the pen. Okay. Now server sends back this number to the hospital. So let's send it back. And the two numbers here are 64 and 22. So 64 and 22. Now let me change the color one more time here, red. So now hospital needs to decrypt this value, right? So for decrypting that, the decryption formula, formula here is equal to, sorry, there's a space here. So it's going to be C0 plus C1 multiplied by S. Let's substitute. C0 is 100 and not 110 actually, is 64 here. Plus C1 that is 22 multiplied by S. That S was 5. So the result is going to be 174. So now we need to do a bit of rounding because anyway, there is some errors there too that added the hospital at the beginning. So if take this a little bit up. Now the hospital needs to divide this by, let's round this to 170. And now 170 divided by that scaling factor, that's going to be 170 divided by 100. So the result is 1.7. So this is not exactly double because if m divided by 2, sorry, m multiplied by 2 would be 0.8 multiplied by 2, and that result would be 1.6. So there is a bit of error, but that can be acceptable, depends on the case. But of course, here is the error is quite high. And if you calculate it is around 8% error, actually. How we can decrease this error? We have to make sure that we choose much bigger delta here. So the delta, instead of being 10,000, it can be 2 to the power of 40, which is much bigger, obviously. So now I'm going to show you in Python how this can be implemented very easily. So hopefully you get a better idea about it. Okay, so here I'm going to show you in Google Colab. So first of all, I import the math library because I'm doing some mathematical operations. Q, that is the ceiling, is 10,000. Delta is 100. Secret value is 5. And I have multiple function. One of them, the encrypt function that is done by hospital. I have a message that I'll define it later. I have a value that choose to be 10, E0 to be 2, and E1 to be 1. And now if you remember, C1 was A plus E1. And of course, everything done modulo Q. And C0 is minus A multiplied by S plus the message plus E0. And again, modulo Q. And finally, we return C0 and C1. And now on the server side, we are multiplying C0 and C1 by the weight of the neural network. That here was 2. And we return the result back to the hospital. Then hospital receives the C0 and C1 and just put it in this equation, C0 plus C1 multiplied by S modulo Q. And we divide that result by delta because we want to get rid of that scale it down again. So here I want to start to encrypt the message that is 0.8 and then send this data to server to double it. And finally, I decrypt it here. If I run this code, you see that the final value is going to be 1.74, exactly as we calculated together too. Of course, if you do rounding, that's going to be smaller, but this is how it works. So the same kind of operation, if you have a bigger model, you just first have to make sure that you scale all the pixels inside your medical image, and then you put them inside one ciphertext. There's techniques that I'll talk about it later. And you send it again to the server after encryption. Thanks so much for watching, and I hope you find this helpful.